Today, I'm pleased to introduce today's session, Working with LLMs at Scale, and our guest speaker, Yujin Tang. Yujin is a developer advocate here at Zillis. He has a background as a software engineer working on AutoML at Amazon. Yujin studied computer science, statistics, and neuroscience with research papers published to conferences including IEEE Big Data. He enjoys drinking bubble tea, spending time with his family, and being near water. Welcome, Yujin.
Yeah, thanks for that introduction, Emily. Hello, everybody. So my name is Yujin. Today, I'm going to be talking to you about scaling LLM applications or working with LLMs at scale. And I've just given this slide the title, The Key to Scaling LLM Applications. So I'll cover a little bit of housekeeping first. So we're going to go over these slides. It's going to be a short walkthrough, maybe 20-ish minutes or so, and then we're going to dive into some code where we're going to work on how you can do multi-document Q&A with LlamaIndex, LangChain, and Milvus. So thanks for coming. I'm going to get started. Okay, so this is me. My name is Yujin Tang. I'm a developer advocate at Zillis. If you have your phones, you can scan the QR code. That will take you to my LinkedIn. You can also email me at eugene@zillis.com or find me on Twitter. But I'm most active on LinkedIn. Oh, what's going on here? Okay. This is a little bit about Zillis. We maintain Milvus. It's the world's most popular open source vector database. These are some links where you can find us. You can go to Zillis Universe on Twitter, LinkedIn. You can look up Zillis. You can find Milvus's Slack here, or you can go to GitHub. And you can go to GitHub and go to milvus-io/Milvus and check out the vector database. Okay, so for this talk today, we're going to start with covering the basics of large language models. We're just going to cover what neural networks are like and how they've evolved into large language models. Then we're going to talk about some of the challenges that are involved with LLMs and using LLMs in production. Then I'm going to introduce this thing called the CVP framework, which is ChatGPT, vector databases, and prompt as code. And we're going to walk through what that looks like and how that helps solve challenges with LLMs. Then we're going to talk quickly about what is a vector database. And I'm going to use Milvus as an example for an example architecture for understanding vector databases. Then at the end, we're going to go through a quick demo, in which is a code walkthrough. So first step, we're going to think about large language models. So you guys have been around for a while. You probably have heard of ChatGPT, and you probably know about OpenAI and Claude from Anthropic and Bard from Google. So these are what are the most, advanced language models that are kind of out there. These are these large language models that are causing a lot of hype right now. So let's take a step back and talk about how we got here and how we got into this idea of language models. So let's step all the way back to 2012. We're going to talk about convolutions, which is, actually they're around before 2012, but they're really popularized by AlexNet. And in this example, we can see that the way that these kind of convolutions work is that they give you context into the tokens next to yours. So in the sentence, Milvus is the world's most popular open source vector database. You can see that the way that this would be set up in this neural network is that you have context into the two tokens right next to yours. From there, we move on to this thing called self-attention, which gives you global context. As you can see, all these arrows are pointing to all of the neurons, all of the words are all the tokens in the sentence. Milvus is the world's most popular vector database. I didn't go through all the words here, but basically every single word in the sentence would have context into every other word in the sentence. So Milvus would know world and so on. But as we know in English, that's not actually necessary. Sentences are built like this. So what we actually need is something like this, which is causal attention, which gives these neurons is access to the, like the word is, access to the words before them. So you can see that all the words point down, which means that all of the tokens further down the sentence have access to the information given by the tokens at the beginning of the sentence. And so this kind of takes us to how LLMs, RNNs, CNNs, how these, transformer models work. Is that there's these different attention mechanisms that are imposed on the neurons based on the architecture, and then it's essentially statistics from there, right? LLMs predict your future tokens. So in these examples, you would be predicting the next token. So this one, we'd be looking for the word database. And that's kind of modeled here. Milvus is the world's most popular vector blank. And if an LLM is producing the sentence, it would say database, and it would say it would say database because it would see that it has the highest probability on there at 0.86 in this example. So because LLMs are stochastic models where they're just predicting the most likely next token, one of the biggest downsides is that there's this thing called hallucination, which is a plausible sounding but factually incorrect response. So this is where the LLM makes up some sort of data based on the data that it's seen, and it says that this is the right next word, basically. So let's walk through a little bit of math. I'm not going to spend too much time on this part. This is mostly, for those of you that are really into the math behind the machine learning stuff. So this is basic statistics, right? We're given some tokens, T0 all the way to Tn plus 1. And then we want to model the outputs based on a probability distribution. So this is, a representation of Bayesian statistics, right? What is the probability of database given all of the words before in the sentence? Is the world's most blah, 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 blah. And this is, these are the indicators, the way that it's written in the math behind the scenes. Okay, now let's look at some of the challenges involved with LLMs. So we're going to look at an example of hallucination just from ChatGPT. And so for the example, this query is, how do I perform a query using Milvus? It'll return something like this, which on the surface looks pretty accurate. You can look at this and say, okay, this looks like Python code. I can see that there's a list here, like some dictionaries here and so on. But if you know the actual code and you go into the docs, you'll see that this is a hallucination and this example is incorrect. And the problem here is basically that this is not actually how you connect to a Milvus server. So later on, we're going to talk about how you do the connection, but I just wanted to show this example as an example of what a hallucination in an LLM could look like. So our solution, the solution to hallucinations, right? There's really two big solutions that are being proposed right now. One is fine-tuning your models, which can be helpful for keeping your models up to date, right? Or can be helpful for training them on your specific information. But these include challenges involving how much data you have, because these LLMs see billions of data points before you get to touch them, before you get to fine tune them. So our proposed solution is you inject domain knowledge into these large language models using the CVP framework, which is what we're going to talk about next. So as I was saying earlier, the CVP framework is ChatGPT, which actually just can be any LLM. We just use it because CVP sounds nice. Vector database, which is the V, and P, which is prompt as code. Okay. So the key idea behind the CVP framework is that we view LLM maps as a general purpose computer with a processor, like a CPU, persistent storage, the vector database, and code, which in this case is the prompt. And later on, when we go through the code, we're going to see how LlamaIndex and LangChain operate as like the processor and the code, right? So LangChain helps you build the prompting with your LLMs, and LlamaIndex kind of wraps around your data. So that's kind of the thought on what this framework for building a scalable LLM will look like. And these are the pieces for it, right? The GPT, any other LLM is the processor, and then vector database like Milvus is like your storage, your ROM, your memory, whatever, and prompt as code is your interface. And so this is just an example of a project that uses CVP. It's called OSS Chat. If you've seen this around, you may have seen this around. This uses This is a chatbot for you to interface with open source software. And what it does is it takes the documents that are available for that open source software, and it creates this layer on top of ChatGPT that uses Zill's Cloud as the vector database. Zill's Cloud is the cloud version of Milvus. It uses Zill's Cloud as the vector database, and then caches all the data that gets asked as more and more users ask questions using GPT cache. And then once you ask a question, it goes and it looks into the vector database. It says, hey, is the information for the answer to this question stored here? And if it is, then we're going to return that, and then we're going to go to ChatGPT and we're going to give you a response. If not, then we don't. Okay, so let's go back to that hallucination example earlier of how do I perform a query using Milvus. And when we use that with OSS chat, we actually get this code back, which shows you the actual way to do a connection. And so this is mainly just an example to show that if you inject the data on top of the LLM, then you can get the correct information back by looking through the data instead of directly asking the LLM, which may not have the correct up-to-date information, the correct or the up-to-date information. Okay, so let's talk a little bit about vector embeddings, and we're going to just kind of talk about why these vectors can help solve this hallucination issue by talking about what vectors are and how you kind of create them. So this framework helps solve this hallucination by injecting domain knowledge, giving the LLM access to domain knowledge, and then doing semantic search on the domain knowledge via your vector embeddings. That's what the vector database is taking care of. So this is a very early on paper. This is a very seminal paper about vectors and vector embeddings. And it's just showing you that you can do math with words, right? The whole idea behind a vector embedding is we're going to use some numbers to represent some sort of object, and then we're going to do math on these objects using these numbers. So we're doing math on words, math on images, math on videos, whatever. And so in this example, it's just showing you if you start with the word queen and you subtract the word woman and you add the word man, you get king, right? Math on words. And most vector embeddings nowadays you're going to see are not two-dimensional. They're usually 700 something, 300 something, 1500 something, 1000 something. They're much larger now. So in practice, the way that we implement this is we just start with our knowledge base, our documents. We transform our documents, we chunk them, whatever. We throw them into a deep learning model. And then we actually get the second to last layer here. Excuse me. So traditionally in deep learning models, you get some sort of output, which is some sort of classification layer usually. And the vector embeddings is actually the second to last layer. And so you take your knowledge base, you run it through a deep learning model, and you just strip the last layer and take the outputs to the second to last layer. That's your vector embedding, your representation of your object, of your knowledge base, and then you put that into a vector database like Milvus. Okay, so what is a vector database, right? We've been talking about kind of how to use it, but let's take a look at what they are. So the way we like to define vector databases here at Zillus or Milvus is a database purpose-built to store, index, and query large quantities of vector embeddings. And Milvus specifically, the advantage of Milvus is that it works really, really well at scale. And the reason why it works really well at scale is because, okay, wait, it's not, next slide. Okay, well, I'll cover that in a second. But let's talk about why you want a purpose-built vector database. So if you want to work with vectors, you don't actually need a vector database. You could just use a vector search library like FAISS, FAISS, or HNSW, or Annoy, or something like that, some sort of vector indexing strategy. Vector databases really provide a lot of different things that you would need on top of vector search if you were to, say, use this in production. If you were to actually use this in practice, you would have things like filtering, filtered searches, chain filters, hybrid searches, backups, replication, scalability, horizontal, vertical scalability, sharding for your streaming data, aggregated search, lifecycle management, upserts, deletes, inserts, stuff like that. And you would also have to be able to handle like high query loads or high insertion deletions, depending on your use case. You need to be able to mess with your recall, your indexing strategy for that. And then, we have, for example, NVIDIA, support with the GPUs, so it operates faster on those GPUs. And we have like really billion scale storage, which is what makes Milvus such a unique vector database. So let's cover some vector indexing strategies, some of these things, these vector search libraries, basically. I'm going to cover a couple of these, and I'm going to dive into the topic of what Milvus's architecture is like and why it's so powerful. So one of the common in vector indexing strategies is called approximate nearest neighbors, or ANOI. It's from Spotify, and basically what you do is you pick any 2 points in your vector space and you just split the space in half. There are some limitations here, like you don't want to be picking 2 points which splits the space into 2 halves, where like you have like one vector on one half. Like that's obviously an issue. But for most cases, just 2 random vectors, you split the space in half, and then you do it again and again and again and again and again until you don't have any more halves to split, or until you have like 5 vectors in each section or something like that. So this builds like a binary tree, basically, and this is how you kind of do that search. Then there's inverted file index, which looks like a Voronoi diagram, and it basically is one. You do like a centroid kind of thing using k means, to cluster all of your points into some number of centroids that you want. And then the way that you would search it is you would start with the n closest centroids and then search into each of those centroids for your closest points. So you can see how this kind of will reduce your search space by allowing you to search smaller portions, kind of similar to ANOI. Then there's HNSW, or hierarchical navigable small worlds. This is a really, really popular one. This is a really popular graph-based vector indexing strategy. And basically what you do is as you insert your data points, and you create like a graph where you point to the closest data point. And as you insert your data points, you generate a uniform random variable that gets assigned to it somewhere between 0 and 1. So, and then you have a cutoff that tells you what layer it's going to. So for example, if your cutoff is 0.9, then you'll have 0.9 only in layer 0. And then if you have somewhere between 0.9 and 1, you get to be in layer 0 and layer 1. And if you get to be, or 0.9 and 0.99, if you have 0.99 and 0.999, then you get to be between layer 0. You get to be in layer 0, layer 1, and layer 2. So basically the layers of these are assigned by random variables, and it's a graph-based index that points to the nearest neighbor. And the way it's searched is you start at the top layer and you find the nearest one, you search all the way down. As you can kind of imagine, this would cut down your search time because A, the index is already built, and B, you get to search less, a very small space from the start, and then kind of a little bit larger space as you go down. The only drawback for this is really that the index is larger than your actual data. Okay, so let's look at what Milvus's architecture is like, and why is Milvus fast? Why is Milvus useful at at scale? With pretty much like a couple hundred vectors, it's really all the same. But when you get to scale, you have to think about things like how big is the space that I'm performing all these vector comparisons on, right? Vectors, when you compare them, when you do a retrieval, you have to do some sort of comparison to the existing vectors, and that requires some sort of matrix multiplication or something like that. So the way Milvus works is that there's these 3 different query nodes, 3 different nodes that spin up every time you want to do something. So indexing is a special node where if you want to do your indexing, this is usually when you add data in, you use the index node, but this is not something that's used very commonly. So There's the other two nodes, which are the data node, which holds the data that you need in memory. And there's the query node, which performs the query and returns to you to the data that you need. Outside of these nodes that do the actual work, the actual processing in Milvus, we have object storage, which is basically, MinIO, S3, Azure Blob, whatever. This is where you store this is where we store the data in the vector database. And you probably don't really need to worry about any of this stuff. So one of the reasons why Milvus is really fast at scale is because it does this thing called segments, where it puts all your data into these 512 megabyte segments, and then it seals these segments every time they hit 512 megabytes. So then when you're querying, and it's able to search these segments in parallel. So then when you query, let's say something that's 100 gigabytes, you are able to do basically 512 megabyte queries. And then, at the end, you kind of coalesce them and compare them based on the segmentations, but you don't need to search the entire 100 gigabyte space, which is what you would do if you didn't have these segmented blocks. So if you think about that, it's you can kind of get it done with 1/200th of the operations needed, plus like a little bit of extra, so maybe more like 1/100th. But as you scale your data size, this becomes more and more noticeable. Okay, so that was, oh yeah, right about on time, so about 20 minutes. So we're gonna look up a quick demo. I'm gonna pull up some code, and then we're gonna do a code walkthrough. So okay. And we're going to build a multi-document Q&A system using LlamaIndex, LangChain, and Milvus, and we're going to use the data. And the data that we're going to pull from is from Wikipedia. And Emily, can you drop the link to the Colab notebook in the chat? Yes. Okay. There it is. There's the Colab notebook. So this is on Colab, so you can go in there, you can follow along. I'm going to make my screen a little bit bigger, and I hope this fits correctly. So for this, all you really need right now to follow along is, Python 3.10 or 3.9. I'm using 3.10. And I would suggest you go ahead, make there some new directory, and then do some sort of virtual environment, blah, 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 and get your virtual environment started. And I'll give you a little bit of time to do that. Oh, actually, I don't have my virtual environment started on here. So what I'm actually going to do. Okay, so now I have my virtual environment there. I thought I had that installed already. I'm going to activate it. And then what we're going to do is we're going to install the libraries that we need for this. So we're just going to pip install LlamaIndex, LangChain, Milvus. I think we need requests, Python.m. That's what I use to handle my environment variables. You don't actually need Python.m necessarily if you want to just throw in your OpenAI API key into your notebook, but I have mine in my .m file, so I'm handling it with Python.m. And then we probably need OpenAI and IPyKernel, which gets automatically installed when you're running through this through. Oh, you know what? I actually missed one. We need NLTK as well. NLTK's like stop words package is like a I believe it's LlamaIndex is using that to do the query decomposition. Query decomposition is this thing where you break down a query into smaller parts, and that's how you do the multi-document Q&A. So let's also install that. So just install it here. Okay, cool. So now we have NLTK. We also need to, and this part I'm just going to copy and paste from the notebook. We need to install the stop words package from NLTK. And this one, you'll sometimes get these errors, these SSL errors, which is why I'm doing it programmatically and not doing it through just starting like a new Python interpreter and doing something there. Okay, let's see. We have a question. Please reshare the collab link. You lost the collab link. Okay, I guess you can reshare it. Yeah. And feel free to stop me if you have any questions as I'm doing this. This is meant to be an interactive kind of workshop. Okay, so now we're gonna do our imports. So from LlamaIndex, we're gonna import a bunch of things. So import. See, first we're gonna import GPT vector store index. Then we're gonna import the simple keyword table index, GPT simple keyword table index. I don't know why this is not highlighting for me. I would have expected this to, did I do llama index? Maybe this will highlight for me. Okay, I don't know why it's not giving me a code completion, but it's not. There's a question in the chat. Is there an associated GitHub repo? There is nothing on GitHub right now. I can put this on GitHub, actually. This should be going on GitHub on Bootcamp, which is Milvus has a Bootcamp repo, and this should be going on there. So I'll put that on there afterwards, and you can check it out on there as well. Why do we need LlamaIndex if we have PyMilvus? So LlamaIndex is what we're going to be using between LlamaIndex is what we're going to be using to do the query decomposition. So what we're actually going to build here. Oh yes, I should probably cover the architecture of what we're going to build. That would have been a good idea. What we're actually going to build here is we're going to take these documents and we're going to load them up into this kind of like these vector stores, right? And then we're going to use a keyword index which is going to be generated by LlamaIndex that's going to actually route you to the correct set of vectors. So that's why we need LlamaIndex, even though we're using PyMilvus. John, I'm going to answer your question later. Please use the Q&A for that. That is a much more general question, and it's not about the code. But so if you have questions about the code, I will answer them as I'm doing this. Okay. Now we're going to import something from LangChain. This is the only LangChain that this is the only LangChain import that we're going to make. And you actually can kind of do something else for this, but we're just going to do this because I like it. Import OpenAI chat. That's right. Okay. Now we're going to set up all the we're basically going to set up our vector database and stuff. So we're going to import OS. We're going to import .m imports load.m. I really wish I had my code completion here. OpenAI load.m. So this loads up the .m file to get my OpenAI key. os.getM OpenAI API key. So that sets up our access to OpenAI, and then we're going to set up Milvus. So from LlamaIndex vector stores, Milvus vector store, and then we're also going to need the actual Milvus. So from Milvus import the default server. And then we're going to start the default server. Start vector store. This vector store with, let's see, host equals localhost 127.0.0.1, and then the port is going to equal default server listen port. Okay, so this should take somewhere in the, that was actually a little bit faster than I thought it was going to be. I thought it was going to be like 10 seconds. Okay. But this basically spins up a local instance of Milvus, our Milvus Lite, which was actually created by, like a third party like maintainer, open source guy who doesn't work at Zilla. So shout out to Matrix G. If you know him on GitHub, give him a shout out. I'm having a version conflict. See which versions, see if you can get your right gRPC IO version on there. If I had more time, I would be able to stop and just kind of, work this out with you live, but unfortunately this is a large session. So what we're going to do now is we're going to get the wiki stuff. So this is unimportant code. This is not technically related to building your LLM app. This is just the gathering the data section. So I'm just going to copy and paste this code. We're getting info on Toronto, Seattle, San Francisco, Chicago, Boston, Washington, DC, Cambridge, Massachusetts, and Houston. And if anybody wants to type in a city to put on here in the next 10 seconds, I'll wait as I paste it into ChatGPT. Try to pick in you guys are, Dubai. Okay, Dallas, Seattle's already on there. So we'll put Dubai on here. And we'll put Dallas on here. Is Dallas already on here? Seattle's already on here. Okay. Okay. Cool. So there's a lot of cities that are being shouted out. But these are the ones that we're going to go with. Okay, so now this part is this is literally the code scraping section. So I'm just going to copy and paste this. I'll walk through this, but you don't need to understand what's going on here. You just need to just copy and paste this code and just put it in here. Okay. Basically, what we're doing is we're going and we're sending a GET request to each of the Wikipedia pages that are listed here in this set. And then we are putting them together, using this is a yield function. This is a generator function. And we're putting all of that text together. And then we're going to save it to a file locally. Okay. So this should only take a few seconds. And we can see what this looks like, right? Boston looks like this. Cambridge, Massachusetts, Chicago, Dallas, Dubai, Houston, San Francisco, Seattle, Toronto, Washington, DC. Okay. So I'm in Seattle. It's my favorite place. I guess I'm currently closer to San Francisco, but I live in Seattle. Okay. So once we have all this, all the documents, now we're going to start getting into building the actual index. Okay. So let's get the docs and we're going to create an empty dictionary for the documents. And then we're going to walk through all of the titles. So for title and wiki titles. To city docs, key titles, and we're going to set this equal to, we're going to use simple directory reader here, simple directory reader. And we're going to read in some input files. So the input files are going to be /data / this needs to be an F string. Title. Jeez. This actually needs to be in a list because the input files expects a list. And then we're going to load that data. Unhashable type list. What did I do? / maybe I have to do this. This is different than what I had before. It was. Okay, what did I do wrong? Did someone see this? Input files, F data / wiki title. Okay. Okay, well, I have this is the right code for this here. So now let's create the service context, the storage context, and the actual chatbot. So for this, we're going to use LLM predictor ChatGPT. And this is going to use, this is basically the chatbot. Like this is the thing that links you to the LLM. And so for the LLM we're going to use here, we're going to use LLM. We're going to set this equal to, this should be OpenAI chat, I believe. Yes, OpenAI chat. OpenAI chat, which is the LangChain piece that we downloaded earlier. Temperature, and we're going to set this temperature equal to 0. And I think we need the model name. Yes, the model name. And that's going to equal GPT 3.5 turbo. Okay. And then we need the service context. Service context is a service context which uses the LLM predictor. So service context. LLM predictor. LLM predictor ChatGPT. Then we need a storage context, which tells LlamaIndex basically how we're storing our files, or how we're storing our vectors. And vector store equals vector store. Okay. And okay, cool. Nothing going crazy here. So now we're going to build the index or the indices. What's going on in chat? Oh, okay. Oh, I had city. Oh, I had wiki titles. Okay, cool. Thank you, Hervé. Sorry. Yeah. Okay, let's build this city index. So city indices, wiki summaries, or index summaries. Index summaries, what I called them before. So the index summaries are the keyword things that are used to that we use to basically route our queries from, for wiki title and wiki titles. We're going to loop through all of these, and we're going to create a GPT vector store index from them. So let's see, city indices, wiki title is okay. So this time I did wiki title, no S. So hopefully it's not going to be mad at me. GPT vector store index from documents. I believe we get the city docs here. City docs, title, service context, storage context, storage context. I believe that's all we need for that part. And then we need to set the index summary. So index summaries wiki title is equal to, I believe we just use an F string. Yeah. Wikipedia article about wiki title. So this is how we get started creating our index. Wow, I'm really glad to see that you guys are helping each other like figure out these errors. Okay, so now what we need to do is we need to get the composable graph object. So what we do here is we just import the composable graph from Llama. And this is the part where we create our the graph that composes the indices, basically. So graph equals composable graph. And we'll start with GPT simple keyword table index, which is basically tells us that we're going to be using this keyword table index for that. And then explore. I believe this would be city indices. Yes. Oh, my nose. Okay. And then we also need the summaries. And then we'll just say max keywords chunk is equal to 50. Is that not the right max keywords per chunk? Oh, wait, that's because I did this wrong. Okay, there we go. Okay, Alex Savashkin, does anybody have the Milvus error? Yeah, if you have that, I would just try starting it up again. If you've started Milvus before and you're like locally and you didn't do like a stop at the end of that file, you're going to run into some errors as some of the threads are going to go. Raj Sam, anyone gone past setting up OpenAI key? Okay, I don't know what to say about that. Jerry Liu, not Jerry Liu, the creator of LlamaIndex. Jerry Liu. Okay. What is the index for underscore blah blah? Okay, so underscores are basically used to represent unused variables in Python. So actually what's going on here is we could actually probably just call city indices dot values. So city indices dot items returns two different, like it returns two things basically, and it returns a key and a value. And we only need the value and we don't need the key. So yeah, that's why. So Daniel Crosby says, playing catch up here, did you run into error Unicode encode error? I was maybe you, I don't know if you're using the same Wikipedia articles I'm using, but that seems like a Unicode character, and you might want to try to see if you can mess around with this to get this to encode into UTF-8. Okay, so let's get through the rest of this. Let's try to finish this up. We're gonna also import the query transform, which is going to be the function that does the actual query transformation. What's going on here? Okay. So the decomposed query transform basically sets oh, wow, that's not a dictionary. Sorry. That sets the LLM to decompose your query to split your query into multiple parts. ChatGPT, and we'll do verbose equals true. You don't actually need to do verbose equals true. This just shows you how the queries are being split. And then the last thing we need to import is the transform engine. And in this case, what we're actually going to start with is some custom query engines. We're going to get that to an empty dictionary. Okay, so let's loop through the indexes. For index in city indices dot values. We'll set a query engine first. So query engine. So we're going to make this the decomposed all the decomposable queries and use a query engine on that in this section here. So index dot as query engine. And then we'll give it the service context. And oh, there's a bunch of questions in the chat. Will the recording be shared on this? Yes. Is there a valid OpenAI? So Raj, yes. The OpenAI key, you have to go to OpenAI to go get an OpenAI API key in order to build something like this. Oh, perfect. There you go, Daniel. And Isaac, yes, the recording will be shared. Okay. And now we're going to also give some extra info. So extra info, and that's going to equal, we're going to give that to index summary, or summary, I think. And that's going to equal index. So this actually just passes an object onto it. That basically gives it the index struct. This the summary of the index. Transformed query engine is equal to the transform query engine. And we're going to set that to the query engine decompose transform. There it is. And we're also going to pass in the extra info transform extra info equals extra info. And finally, the custom query engine. Just one. Oh no. Oops, custom query engines. Index dot index ID. ID. So this actually will just return a string that is the like an index ID basically. And that is the transform query engine. Okay, so I'll let that go, and then I'll answer some more questions. Quick question: does OpenAPI provide API access to GP4 model paid? Yes, it is paid. Is the query engine going to be able to add weights to the wiki pages to filter better? I think you can do that, but we're not going to do that in this. We're just going to get it to work in a very basic level first to make it so that it can decompose the queries. If you want to try to add weights to things, you can go look into the LlamaIndex docs and see how you can do that. Okay, custom query engines. And we're going to go to graph. So this is the graph that we created earlier, right? This is the graph that starts with a keyword index, index ID. So that's equal to graph dot root. Oh, is it root ID or root index? So we're using root index dot as query engine and retriever mode. Is that not right? Retriever mode. It's not happy with me about this. Well, response mode. Tree summarize. Service context. I think storage context here as well. Yeah, storage context. Okay, so I'm actually going to go up here. We're going to change this. I think this also should be given a storage context. Okay. So now we have this custom query engine, and then all we need to do is we need to make the decomposition engine. So just a couple more lines of code. And then I will answer your questions. Let me just get this couple of lines of code on here so you can kind of see how this works. Graph.as query engine, and we'll just need to pass in the custom query engines. So custom query engines equals custom query engines, and that should work. Okay, so now we should get a response, and that should equal query engine decomposers dot query. And I'm actually going to let you guys type in a response. Ask about, any of these cities here. Maybe we'll ask it to compare and contrast the weather in Seattle and Dubai or something like that. It's query engine. Where does GPT cache fit into this? We're not using GPT cache in this one. GPT cache is an open source cache for your GPT apps that uses, Milvus, but in this one, we actually aren't going to be caching anything because we're not doing any examples where we're pinging the LLM enough to have like an FAQ. Can Milvus support adding weights to docs, say on author date? I don't think so. Okay, so let's compare and contrast the weather in Seattle. Compare and contrast the weather in Seattle and Dubai. And now we wait, and it's going to show us what the breakdown of the question is, and then it's going to give us an answer. Oh, we'll actually have to print out the response in a second, but let's see. Print response. We'll just load that up and let it go. Okay. And then there it goes. It tells you Seattle receives precipitation on 150 days in a year, often has light drizzle. Exact annual rainfall in Seattle is not provided. Dubai has a high average temperature, et cetera, et cetera, et cetera, et cetera, et cetera, et cetera, blah, blah, blah. Okay, so, therefore the weather in Seattle is characterized by frequent precipitation, while Dubai has high temperatures throughout the year. Yeah, so it's raining in Seattle and it's hot in Dubai. Do you have a solution for governed data on vector database? I'm concerned about PII data to leak. Do I have a solution for governed data? I mean, you can host your own data. Like you can, like Milvus can be used to access your local data if you want to do that. Otherwise, you can just use Zillow's cloud. But if you're concerned about PII stuff, maybe you just want to host your own data and just host it locally and use something like, maybe not Milvus Lite. Milvus Lite is, mainly used for this kind of like building like this kind of proof of concept in a notebook. Maybe you want to use like Milvus standalone, or you probably want to use Milvus standalone, and you can do that with Helm or Docker Compose. Emily, if you have those links, it'd be great to be able to drop those in the chat. So yeah, that was all of this basic tutorial on how to create your own multi-document Q&A. And for the rest of this time, if you have some debugging help that you need, I can kind of take a quick look at anything that might be simple, or if you have any questions about vector databases, feel free to ask. Okay, lots of questions. Do you think this could also be used for recommender system? You mean vector databases? Because that is actually one of the primary uses of vector databases in production. For example, eBay. What would be the solution to cite the source documents? You could just have it return. Sorry, my nose is itchy. You could have it set up so that it returns the source document, I guess. You could like save the link if you wanted to, and then just have that return with your answer. Thanks, Eugen. Thanks, Hervé. This is amazing what you showed. In this example, are we fine-tuning GPT 3.5 Turbo model with our Wikicity datasets, and only after that GPT 3.5 Turbo is able to answer? Okay, so casing, we are not fine-tuning anything. We are doing data injection. So what's happening here is this is your LLM, it's like this like little big box. And on top of that, we have a vector database. And on top of that, we have the querying and the indexes. So what happens is we take some data and we put it into the vector database, and then you come in, you hit this query box, and the query goes into the vector database, and it says, hey, do I have an answer? And it says, okay, I have an answer. Oh no, so actually it's a little bit more complicated than that. The query goes in the index, and then the index calls GPT and says, how do I break this query down into multiple queries? So for example, compare and contrast the weather in Seattle. Then GPT responds and it says, okay, what is the average rainfall in Seattle? Or, what is the average temperature in Dubai? And then it uses that and it pings the vector database with these questions, and then it compiles these questions together, and then it uses ChatGPT to get the answers from those questions and formulate a real response and sends it back to you. So there's no fine tuning going on. It's just data injection. About PII, my take is if your system doesn't have public endpoints, slipping of NPI would be low and can use DLP cloud solutions. I have no comments on this. I don't know what this is. I know you have covered, but can you please help me understand what is LlamaIndex and what's the role here? Okay, so LlamaIndex is a framework for interacting with your data and an LLM. So in the CVP framework slide that I showed earlier, LlamaIndex is like the C and the P. So the role here is that LlamaIndex is what we use to create these indices, like this keyword index, this vector store index, and what we use to route those queries through to the right vector stores. How many tokens involved in this scenario? Yeah, I actually don't know because I didn't put the token counter here. Now, I'm sure there is actually a way to put the token counter here because LangChain allows you to count tokens, but I don't know because I didn't do it. Okay, eBresci. Answer live. Is there a way to know if the reply was generated using data from the previous existing knowledge of the model and what is fetched from the vector database? So in this case, it is using data just from the vector database. What you could do is you could like put into your code somewhere that like, oh, if you don't find this, like some sort of clause that just says like, if you don't find this in the vector database, ping the LLM. But what we're actually doing is we're just using the LLM to break down the query into different into like the decomposed queries, I guess, into like the simpler queries, and then we're using it to formulate the answer. Surya Pavan, can you query directly without vector database in the middle? What is the benefit we are getting on top of GPT? Is indexing necessary here? Can I query? I'm going to answer this live. One sec. Can I query GPT directly? I mean, technically, yes. Do you need a vector database? Is indexing necessary? So you like the benefit that you get on top of GPT is that you get to inject up-to-date knowledge and like domain-specific knowledge. So, I will yield here that like perhaps cities are not the most domain-specific things, but it's not like I can go and grab like very specific knowledge to show as a public example. And is indexing that, I mean, indexing is you have to do this anytime you have vectors and anytime you want to compare things semantically. So for example, if you ask GPT this question, it might be able to get it. But maybe you can ask something, maybe we can ask something like compare and contrast the airports, right, in Seattle and Dubai. And in this case, maybe there's been a new, I don't actually know, maybe there's been like a new airport built since 2021, in which case we would need that updated knowledge, and querying GPT alone would not be enough. In that case, you would definitely need to have that vector indexing. Does this data injection minimize undesirable hallucinations? Yes, that is the whole point. Oh, Emily. Okay, well, anyway, that is the whole point. The idea is that you basically have all of your data ready, and you just query your existing data, and then you never go to ChatGPT and ask, hey, blah blah blah, can you do this, can you answer this question? ChatGPT just helps you break down the query and formulate a response. Can you use this method to validate GPT output? Validate GPT output. I guess you could. Yeah, if you have all the right answers and you ask GPT and you want to, make sure that GPT has the right answers, you could use this kind of method. Do we still need to add additional guardrails on how accurate this is? Additional guardrails for, I mean, maybe like, for example, like, GPT is still biased, it's still trained on data on the internet that is still biased. So in that sense, guardrails, yes. In other sense, like we're not asking it to do any, we're like limiting the prompts that get sent to it. So it's not like we're asking it to take over the world. So no need for guardrails on that. What are the biggest mistakes companies make while building ingestion pipelines for the data from multiple sources to Milvus? Julian, that is a great question, because that is something that I've also personally been thinking about, because I'm like, hey, these apps are really cool, but how do we keep them updated? How do we keep the data updated? And I actually don't know the answer to that question. And I wish I could tell you, but I don't know the answer to that question. And that is something I'm also curious to find out myself. Can we restrict bad questions? Can we filter wrong queries? I mean, yeah. It's your system. You can always put in whatever things on there that says like, hey, like don't answer questions about Dallas. Don't like that area. Whatever. Will the tool still hallucinate if you ask prompts out of the injected data from eBrushy? No. Hamza, at what point does fine-tuning make more sense than context or data injection? If you have a lot of money and a lot of data, and you're willing to fine-tune your model often. Ron, some guardrails come from ingestion from corporate sources that have already been improved from past marketing and sales language. This isn't a question. I don't know what to say about this. Okay, so it looks like that's all the questions that we have, and we're also approaching time. So this was a good session. I hope this was a good session for you guys, and that you were able to, build a cool app. And if you have any questions, feel free to reach out.
Thank you, everyone, for joining us. And thank you, Eugen, for this great session. We hope to see you all next time. If you want to see our upcoming calendar of events, check out zillis.com/event. And we hope to see you on a future training. Thanks so much, everyone.